In this video, we're going to calculate the wavelength of light emitted by a hydrogen atom as an electron relaxes from a higher energy state down to a lower energy state. And so what we have drawn right here now is a very simplified atomic orbital energy diagram, where the electron is currently sitting in the n=4 shell. And so when that electron relaxes down to the n=3 shell, a photon is going to be emitted as it's going from a higher energy state down to a lower energy state, and that extra energy has to go somewhere. And so to be able to calculate that energy, what we're going to do is use a modified Rydberg equation. As we already know, the Rydberg equation states that the energy of a shell is equal to the Rydberg constant, which is negative 2.178 times 10 to the negative 18 joules, times z squared over n squared, where z is the atomic number of the one electron atom, and n is equal to the shell at which the electron currently resides, or at which that orbital exists. And so if we take that for those two different shells, and we combine it together, what we get is that the change in energy upon relaxation is equal to negative 2.178 times 10 to the negative 18 joules times, and now this is all going to be as its own separate brackets, z squared over n squared final, where n squared final is the shell that the electron is going to reside in at the end of this transformation, minus z squared over n squared initial, which is the shell at which the electron initially resided. So if we plug in all of our different values, for z we will have a value of 1, for n final we will have 3, for n initial we will have 4, and if we calculate all of that up now, what we get is negative 1.059 times 10 to the negative 19 joules. And that's the energy of that photon emitted. Now, to calculate what that wavelength of that light is going to be, we'll use the equation that we have previously used, where lambda is equal to hc over E. And so if we plug in our values for h, which is Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds, times the speed of light, which is 3 times 10 to the 8th meters per second, over the energy that we previously calculated, which is 1.059 times 10 to the negative 19 joules, we can see that the joules cancel out and the seconds cancel out, and the wavelength of the necessary light is 1.877 times 10 to the negative 6 meters, or 1,877 nanometers. So to recap, in this video we calculated what the emitted photon's wavelength is going to be when an electron relaxes down to a lower energy state.